Welcome to this video lecture on regression analysis. When we carry out a regression analysis, we are interested to know if there really is an underlying relationship between the predictor x and the response y. Now, the population regression equation states that y equals alpha plus beta times x. Beta is the slope of the population regression line. When we take a sample, we have a sample value b, which estimates beta. Therefore, how can we be sure that the value of beta in the population is not 0? Because if it's 0, then the regression equation is useless. We address this question by testing the hypothesis that beta equals 0. And if the p-value we obtain is less than 5%, we reject the null hypothesis that beta equals 0 in favor of the alternative, that beta is non-zero, and therefore there is a relationship between x and y, and x, the predictor, is a useful predictor of the response y. That's the most important hypothesis to test, whether beta is 0 or non-zero. But there is a second hypothesis that is also interesting to test, and that is the hypothesis that alpha equals 0. Alpha equals 0 would mean that the population regression line passes through the origin, and that therefore y and x are directly proportional. And again, we can test this hypothesis by observing its p-value and seeing if that p-value is below 5%. If the p-value is below 5%, then we reject the hypothesis that alpha is 0, and we can assert that the line does not pass through the origin. If the p-value is above 5%, then it may be the case that the line passes through the origin, and therefore y and x may be directly proportional. We use a regression equation to predict new values for y. We supply a value for x, and we predict or estimate the corresponding value for y. And the value for y that we obtain using the regression equation is called the fitted value, or the fit. Of course, no certainty attaches to this prediction because it's possible that our regression line is not perfect because it's based only on sample data. So we can also provide a confidence interval. Using the software, we have a confidence interval which estimates with 95% confidence what is the average value of y that corresponds to that particular value of x. And if we're interested not just in the average value of y, but in a particular value of y corresponding to some individual x value, then the software provides a prediction interval, which estimates with 95% confidence an individual value of y that corresponds to a particular value of x. Graphically, the confidence interval estimates the height of the line for that value of x, while the prediction interval estimates the height of an individual point for that value of x. The regression line is called a least squares line. And the reason for that is as follows. The purpose of a regression line is to estimate values of y. Therefore, the errors in estimating y should be as small as possible. Now, the errors in y are the vertical distances between the points and the line. These errors are squared so that they become squared errors, and then they're added together, which is called sum of squares. And that quantity should be as small as possible. So the sum of the squared errors should be minimized. Hence the name least squares. There are assumptions that apply to a simple regression analysis, and those assumptions are threefold. The first assumption is that there is an underlying linear relationship. That is to say, the average value of y does have a linear relationship with x. Now, of course, the individual values of y don't lie on a straight line. There's a certain amount of scatter that we will observe in the graph. However, we assume that the average value of y for each x value does lie on a straight line. So if we could graph average y against x, we would get a straight line. And the reason why some points are above and below is that those individual y values are above or below their mean. The second assumption is that the errors in y are normally distributed. That is to say, if the value of x is fixed, then different values of y will arise, the average value will be on the line, but the distribution of the y values will be normal. That is, there's a single peak, which is at the line, and a tail that extends above and below. And the third assumption is that there is constant variance. That is, that the standard deviation of the y values is the same for every different value of x. Now, as the values of x change, the values of y change. So the mean value of y changes when x changes. But we assume that the standard deviation of y does not change when x changes. And that's the constant variance assumption. You can read more about this in the textbook in section 6C, Regression Analysis.